Hey there, it's Shannon Matchick-Myers, and today we'll be checking out orthonormal bases and the Gram-Schmidt process, which enables us to make a base that is not orthonormal, orthonormal. So let's check it out. Consider the standard basis for R3, which was what? Do you remember? Beautiful. 1, 0, 0, 0, 1, 0, and 0, 0, 1. Cool, cool? All right. This set is the standard basis because it has useful characteristics such as the three vectors in the basis are unit vectors, and they are each mutually orthogonal. And what did that mean again? If you evaluate the inner product of each of the vectors two at a time in the basis here, you'll get 0. Awesome. Now, for this section, we're going to just be using the dot product, which remember is the Euclidean inner product space. Cool, cool? All right, let's get to it. Definitions of orthogonal and orthonormal sets. A set S of a vector space V is called orthogonal when every pair of vectors in S is orthogonal. If, in addition, each vector in the set is a unit vector, then S is called orthonormal. For S equal to the set of vectors V1, V2, all the way down to Vn, this definition has the following form. So orthogonal, you just have one condition, and that condition is the inner product of Vi and Vj, and those are both vectors, is equal to 0 for I not equal to j. Groovy? All right, orthonormal will have an additional condition. So it has this first condition, the inner product of Vi and Vj is 0 for I not equal to j. And the second one is going to be, awesome, the magnitude of each vector in the basis is 1. And I is going to equal to what? 1, 2, dot, 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 all the way down to n. Groovy? All right, so if S is a basis, then it is an orthogonal basis if it meets the first definition, or an orthonormal basis if it meets the second definition. Theorem 4.10. Orthogonal sets are linearly independent. So if S equals the set of vectors V1, V2, all the way down to Vn, is an orthogonal set of non-zero vectors in an inner product space V, then S is linearly independent. So it's kind of a groovy little proof. Let's check it out. If we've got, let's see, the vectors have been defined, but why don't we let Ci belong to the real numbers? They'll be our scalars for I equal 1, 2, dot, 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 all the way down to n. Okay, so let's check this out. So let's think about this. I mean, if we look at C1V1 plus C2V2 plus dot, dot, dot plus CIVI plus dot, dot, dot plus CNVN, right? Well, in order for this set here to be linearly independent, what would happen? It would equal to the 0 vector, and we get the trivial solution, right? So we're going to do something a little bit like that. I mean, this is kind of where we're starting with. But now we want to look at the inner product because we know this is an inner product. So if we take the inner product of this linear combination of the vectors in V with some VI, right, that's in that set. And if we set it equal to the inner product of the 0 vector with VI, let's check out what we get. Well, wouldn't we have C1V1, and that'll be, we'll do the inner product of that with VI, plus the inner product of C2V2 with VI, plus dot dot dot, so I'm just applying properties for inner product, plus the inner product of CIVI with VI, plus dot dot dot, plus the inner product of CNVN with VI. And what will we get for the inner product of the 0 vector with VI? Beautiful, we'll get the scalar 0. Groovy? Well, continuing, we can take the C1 out and multiply it to the inner product of V1 with VI, plus, good, C2 times the inner product of V2 with VI, and continuing in this way till we get to Ci times the inner product of Vi with Vi, plus dot dot dot, plus Cn times the inner product of Vn with Vi, and that's all equal to the scalar 0. Okay, well, what do we know? We know that for I not equal to j, that the inner product is going to be 0, right? Because we've been given that S is an orthogonal set of non-zero vectors. So we'll have C1 times 0 plus C2 times 0 plus dot 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 plus Ci, and then we don't know what this is going to be. We know that this is not going to be 0 because Vi would have to be the 0 vector, and these are non-zero vectors. So we'll just keep this going here, all right? And then we'll have plus dot 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 plus Cn times 0, and that's equal to the scalar 0. And we were able to do this because S is orthogonal. All right, so next up, well, we'll have 0 plus 0 all the way down until we get to what? We'll just have Ci times the inner product of Vi with itself has to be 0. Good so far? Well, how else could we write the inner product of V with itself? Beautiful. We can write that as the magnitude of Vi squared, right? So we'll have Ci times the magnitude of Vi squared is equal to 0, but Vi is not the 0 vector, right? So we can say, let me go over here, since Vi is not equal to the 0 vector, it must be true what? That Ci is equal to 0. And what does that imply? Therefore, S is linearly independent. Cool, cool? All right, so moving on, let's look at the corollary. This theorem is a corollary. If V is an inner product space of dimension n, then any orthogonal set of n non-zero vectors is a basis for V. Consider this following set in R4. Determine whether the set of vectors is orthogonal. So what do we need to do for that? Beautiful. We need to find the inner product of what? Each of the vectors in the space. And in this one, let's see, I should have said use the Euclidean inner product. In other words, the dot product. So let's check it out. Root 10 over 10, 0, 0, 3 root 10 over 10, dot, 0, 0, 1, 0 is equal to what? Beautiful, 0. And then root 10 over 10, 0, 0, 3 root 10 over 10, dot, 0, 1, 0, 0 equals, awesome, 0. And then root 10 over 10, 0, 0, 3 root 10 over 10, dot, negative 3 root 10 over 10, 0, 0, root 10 over 10. Let's see what that is. That'll be a little more involved. We'll end up with negative 3 times 10 over 100, right? And then plus 0, and then we'll have plus 3 times 10 over 100, so those will zero each other out, so we'll get 0. Cool so far? Alrighty, now let's see, we'll have 0, 0, 1, 0, dot, 0, 1, 0, 0. That's going to be what? 0 plus 0 plus 0 plus 0. So that's 0. And then 0, 0, 1, 0, dot, negative 3 root 10 over 10, 0, 0, root 10 over 10. And that will also give us 0. And then we will have what? 0, 1, 0, 0, dot, negative 3 root 10 over 10, 0, 0, root 10 over 10. And that's going to be what? 0 plus 0 plus 0 plus 0, which is 0. So, what do you think? Yes, right? That's our answer, because each pair is orthogonal. Each pair of vectors is orthogonal. So if the set is orthogonal, then determine whether it is also orthonormal. So here, well, you could go through and you could find the magnitude or length of each of these vectors and see if it's 1, right? So that's one way you could do it. Or you could use this theorem here. We know that the dimension of our 4 is beautiful, 4, because there's 4 vectors in the standard basis. So we also have this set which is orthogonal, and so therefore we know that this set that we were given, call it S, set S, we know that this is an orthonormal set. But just in case you forget, you can do it the longer way. So the magnitude of the vector root 10 over 10, 0, 0, 3 root 10 over 10 will be equal to what? The square root of 10 over 100, if we square, and then plus 0 plus 9 times 10 over 100, which would be 90 over 100, and that is indeed equal to 1. Cool, cool? And then the magnitude of, hopefully you can see these other ones very quickly, 0, 0, 1, 0. Do you see that that's going to be equal to 1? And then the magnitude of 0, 1, 0, 0, same thing, will equal to 1. And then the magnitude of, what's that last one, negative 3 root 10 over 10, 0, 0, and then root 10 over 10 will be equal to the square root of 90 over 100 plus 0 plus 0 plus 10 over 100, which indeed is 1. So the answer to this question would be yes, because all of the magnitudes are 1 for each of the vectors. Okay? So now determine whether this set is a basis. Well, here, all right, let's use this theorem, right? The dimension of R4 equals 4, and S is orthogonal. Therefore, S is a basis for R4. And that is by theorem 4.10. And really in this one, these are general directions. I should have said here, for us, Rn equals R4 from the problem we were given. All right? Okay, so moving on to the next one. Theorem 4.11, coordinates relative to an orthonormal basis. If B equals this set of vectors, v1, v2, all the way down to vn, is an orthonormal basis for an inner product space V, then the coordinate representation of a vector W relative to B is. So we'll have W equals the inner product of W with V1 plus the inner product of W with V2 plus dot 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 plus the inner product of W with Vn. So it's actually pretty cool because here this is like your C1, C2, and then all the way down to your Cn, like we were looking at. So let's look at the proof for this. Since B is a basis, that's been given, right? For the inner product space, V. Well, what do we know? Beautiful. There has to exist unique scalars C1, C2, all the way down to Cn, such that W equals the linear combination of the vectors in the set. So you'd have C1 times V1 plus C2 times V2 plus dot 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 plus Cn times Vn. All right. Actually, let me put that middle term. We'll be using that. Plus Ci times Vi plus dot 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 plus Cn times Vn. Cool so far? All right. So now let's look at the inner product of W with Vi. Well, that's going to be kind of like that last one, right? We'll have C1 V1 plus, we're just replacing what W is. So plus C2 V2 plus dot 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 plus Ci Vi plus dot 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 plus Cn Vn, and then that that sum of vectors, we'll have the inner product of that with Vi. So all we did here was we replaced W with this sum right here, because that's what W is. Cool, cool? Okay, well, let's see what we have then. Just like before, we can use properties of the inner product to rewrite this as what? Beautiful. C1 times the inner product of V1 with VI plus C2 times the inner product of V2 with VI plus dot 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 plus CI times the inner product of VI with VI plus dot 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 plus CN times the inner product of Vn with Vi. Cool, cool? All right, well, what was given? This is an orthonormal basis, right? And so because of that, we know it's orthogonal, correct? So we're going to end up having the inner product of W with VI is just going to be beautiful. CI times the inner product of VI with itself, because all of these other ones will zero out. You'll get 0 for that inner product, 0 all the way down to CN will be 0. And the only one left will be the one we wrote. Cool, cool? And that happened because B rather, is orthogonal. And we know it's orthogonal because it's an orthonormal basis. So, all right. Whoops, sorry. And then, so now, what are we going to get? Well, this will be the inner product of W with VI is equal to CI times, well, isn't that equal to the magnitude of VI squared, right, using properties of inner product? And then what will we get? We will get the inner product of W with VI must be equal to CI times what? 1. Beautiful. And that's because B is what? Orthonormal, right? All right, so then what are we going to have? What's left? Awesome. The inner product of W with VI equals CI. Isn't that awesome? And we're done. We've shown what needs to be shown. All right, so what does that mean? The coordinates of W relative to the orthonormal basis B are called the Fourier coefficients of W relative to B. So people take an entire, master level class on Fourier analysis, if you're interested in that. All right, so the corresponding coordinate matrix of W relative to our orthonormal basis B is W equals the matrix that consists of these inner products. So the inner product of, W with V1, W with V2, all the way down to the inner product of W with Vn. But what is that going to be? It's just going to be equal to C1, C2, all the way down to Cn. Pretty groovy, huh? Okay, so for example 2, show that the set of vectors given 2, -5, and then 10, 4 in R2 is orthogonal, and normalize the set to produce an orthonormal set. So here we go. Now this is just kind of a stepping stone here, and then we'll use the, I should have added to these directions, use the Euclidean inner product, which is our dot product. We're starting out with an orthogonal set, and we just need to show it's orthogonal. But here we've got our next step of learning today will be to find out how we can take a set that is not orthogonal and orthogonalize it. All right? So that's coming up soon. Here we go. So let's show it's orthogonal. We only have these two vectors, right? So the dot product will be, let's see, 2 times 10 is 20, and then plus negative 20, which is 0. So we've shown they're orthogonal. This is an orthogonal set. Okay, well, what do? How do we normalize each vector? Beautiful. We divide each vector by its magnitude, right? So if we wanted to call each of these vectors like v1 and v2, right? u1, right, would be v1 over the magnitude of v1, which would equal to 2 negative 5 over the square root of what? 2 squared is 4 plus negative 5 squared is 25. And so that ends up being root 29. So what will we have for our vector? 2 over root 29, comma, negative 5 over root 29. And then what would our u2 be? Awesome. We'd have v2 over the magnitude of v2, which will be 10/4 over the square root of what? 100 plus 16. Cool so far? I think 4 divides 116. So we'd end up with a little algebra getting 10/4 over 2 root 29, which is what? Awesome. 5 over root 29, comma, 2 over root 29 for our vector. So this new set of vectors, okay, call it B prime, I guess, is orthonormal, and it consists of 2 over root 29, comma, negative 5 over root 29. And then the next vector was 5 over root 29, comma, 2 over root 29. So this basis is orthonormal. Okay? Next up, find the coordinate matrix of x equal to negative 3, 4 relative to the orthonormal basis. B equals root 5 over 5, comma 2 root 5 over 5, and then negative 2 root 5 over root 5 over 5 in R2. We're going to use the dot product as the inner product. So, let's see what we would do. Well, if we call this, V1 and V2, we're using that theorem, right? So we know that the coordinate matrix of x relative to this orthonormal basis B is going to be the matrix made up of the inner products of x with each of these vectors. Cool, cool? Okay, well, that's going to equal to the dot product, because that's what we're using as the inner product, right? And x, remember, is given right here. So we'll have negative 3, 4 dot root 5 over 5, and then 2 root 5 over 5. And the second one will be negative 3, 4 dot negative 2 root 5 over 5, comma, root 5 over 5. All right? So, well, what will we get? That will be equal to, well, negative 3 times root 5 over 5 is just negative 3 root 5 over 5. And then it'll be plus 8 root 5 over 5 for the first one. The second one will be 6 root 5 over 5 plus 4 root 5 over 5. And this is going to simplify to be negative 3 root 5 over 5 plus 8 root 5 over 5 will give us what? Just root 5. And then 6 root 5 over 5 plus 4 root 5 over 5 gives us 2 root 5. Groovy? All right. And here we are. Cool, cool? Okay. So now, here we go. The Gram-Schmidt orthonormalization process. So this is what is going to happen here. We start out with some basis made up of these vectors v1, v2, all the way down to vn. It's a basis for some inner product space v. That should say space. And then here, this b prime, this basis b prime, is going to be orthogonal, right? We're going to set this up where it's orthogonal. So b prime will be made up of these w vectors, w1, 2, all the way down to wn. And this is what is happening, okay, with this. Does this look familiar at all? I think we learned it in the last section. Isn't this equal to what? Beautiful. The projection of v2 onto w1. Cool, cool? And remember, it's orthogonal, the orthogonal projection of v2 onto w1. So what we're doing here is you just set your first vector, right? You just set one of them. And you say, okay, my first w is going to be v1. That's what's going on in this step, right? And then after that, you take that next vector, v2, and you're going to subtract from that the orthogonal projection of, this was v2 onto w1, right? So the orthogonal projection of the vector you're dealing with onto the vector from before, w1, that you found before. And then as you go on, you keep subtracting these projections because you're going to have to do the orthogonal projection of the given vector on each of the prior new vectors. Okay? So it ends up looking something like this, right? If you start out with just 3 random vectors, all right? So let's say you have, something like this. You have, this is our vector v1, and then we have whatever, some other vector v2. Call it like this. You can say this is vector v2. And then we'll have another vector somewhere over here. And we'll call this one v3. All right? Our very first thing is going to be, okay, well, why don't we let this vector here, vector v1, that's going to just be my w1. Okay? I got to start somewhere. So let's start there. Now, then what I do for my next my next vector, right? To find W2, what do? Well, I've got to take my vector V, which one? V2, right? And from that, I got to subtract the orthogonal projection of V2 onto W1. So what it ends up looking like here, right, is, well, it's going to be orthogonal, right? So isn't it going to look something like this? I'll end up getting, I don't know, I'll use this color here. So I'll end up being orthogonal. So I'll form a right angle to, I'll form a right angle to my V1, or my W1 rather, and then it's going to, this vector V2 will project onto W1, orthogonally project. So now what we have is we have our vector W2, all right, our vector W2, and then we'll have also gotten this distance here, right? That's the orthogonal projection. And then when I do the subtraction, okay, what's going to happen is I'll have this distance, here, right? Like this. We'll call this distance 1. Okay? And then what's going to happen? Well, for this other vector here, I'm not only going to be utilizing my new vector W2, which looks something like this, right? This new vector W2, right? And actually, we don't even need to look at V2 anymore because V2's out of the picture. So we'll just kind of scribble out V2 here. All right, and then what will happen is we now have to do that orthogonal projection. This V3 vector has to orthogonally project onto W1, and it has to orthogonally project onto W2, okay? So when we do this, well, let's check it out. So and remember, we're finding the V3 minus, right? The orthogonal projection of V3 onto W1, and then we're also going to subtract from that the orthogonal projection of V3 onto W2. Cool. W3 has to be what? Orthogonal to both W1 and W2. So in order to do that, it'll look something like this. So this would be W3, okay? And then you're going to have these distances, right? So you'll have, and again, that comes, let me move where the V3 is. So you can see it better. So this was my V3, okay? So you'll end up having, one distance that goes, again, both of them will go from, they'll both go this bigger. You'll have one distance that goes something like this. So that would be distance 2. And then we'll have another distance that goes something like this. go something like this on the axis there. And this one will be this little thing here. This piece will be distance 3, and just this piece of it. Cool, cool? And this here is the axis. Going down, and then you'll have your P3. Cool, cool? Okay. So, long story short, this is our, and we didn't need this one, sorry. This is the kind of setup, and you keep going on and on and on until you were done. Okay, so this is this is what we do in order to get each of the vectors to be mutually orthogonal. All right, but we don't have an orthonormal basis yet. After you do all that, okay, after you get done finding all these W's, right, finding all these W's right here, you will have found an orthogonal basis, right? So this is an orthogonal basis. But the final step, okay, is going to be to find this one here, this one here. So this set B prime is orthonormal, all right? And another really cool thing is that the span of V1, V2 down to Vk is equal to the span of U1, U2 down to Uk for k equal to 1, 2, all the way down to n. Groovy? All right, so let's take a look at example 4. All right, so example 4, we need to apply the Gram-Schmidt orthonormalization process to transform this given basis B for a subspace in R3 into an orthonormal basis, and we'll be using dot product again. And just for the ease of grading, let's go ahead and do the vectors in the order they show up. All right, you don't have to, but it makes it easier on me. So here we go. If we're going to set, so if this is vector V1, vector V2, and vector V3, we're going to set vector V1 equal to W1 to give us our starting point, and that's going to equal to 1, 0, 0. Cool so far? All right, so remember, W2 then is going to be equal to what? Good. V2 minus the orthogonal projection of V2 onto W1. Cool, cool? All right, well, what is that? That is going to equal to, so we'll have W2 will equal to V2 minus what? The inner product, so in this case, the dot product of V2 with W1 over W1 dot W1, and then times the vector W1. Good so far? And so that will equal to, well, what was V2? Beautiful. 1, 1, 1 minus, we need to find the dot product of V2 with W1, so that's going to be 1, 1, 1 dot, and W1 was 1, 0, 0, divided by the dot product of W1 with itself, and then times W1. Okay? So W2 will equal to 1, 1, 1 minus, so that dot product will just be Good. 1. And the magnitude, or sorry, the dot product of W1 with itself will also be 1 times 1, 0, 0. And so W2 will end up being what? 1 minus 1 is 0. And then we'll have 1, 1. Cool, cool? And this is what we substituted in. So where were we here? W1, all right? That's all the W1s. And then we got our our V2 was here, okay? And that's where this came from. Groovy? And then, oh, and then here we had more W1s, right? Right here. And right here. Okay? And now we have this W2. And this W2 is, I'll do this one, gold. Okay? All right, so for W3, oh, and these are vectors, my bad. Sorry. So for W3, we now have to do what? We take our vector V3, we subtract from that the orthogonal projection of vector V3 onto W1, and then we also subtract the projection of vector V3, the orthogonal projection of vector V3 onto W2. Cool, cool? All right, so let's see what happens. W3 will be equal to, so our V3 was 1, 1, negative 1. And then we're going to subtract the orthogonal projection, so that'll be what? V3 dot W1 over the dot product of W1 with itself, which we already found before, and then times the vector W1, and then minus the dot product of V3 with W2 divided by the dot product of W2 with itself times the vector W2. Cool, cool? All right, so here we go. W3 will be 1, 1, negative 1, minus 1, 1, negative 1, dot 1, 0, 0, divided by 1, 0, 0, dot 1, 0, 0, which we found to be 1 already. And then times 1, 0, 0, the vector. Minus, what's next? Well, we got to use V3 again. So 1, 1, negative 1, dot, what was W2? Beautiful. 0, 1, 1, divided by 0, 1, 1, dot 0, 1, 1, times 0, 1, 1. Cool, cool? And so we will have W3, the vector W3 will be 1, 1, negative 1, minus. So this will again be 1 over 1, and then times 1, 0, 0, and then minus, we'll have 0 plus 1 minus 1. So we'll get 0 over, well, it doesn't matter what that is, but it happens to be 2 times 0, 1, 1, the vector, but that'll be the 0 vector. So then we'll have W3 is, I'll write it out just for the sake of showing you everything. 1, 1, negative 1 minus 1, 0, 0 minus the 0 vector. So our W3 will be 0, 1, negative 1. Cool, cool? All right, so here's how everything matched up where do we have our W2s? W2s were all here. And then our W1s were all here. All right, and then we got our V3 was this vector here. All right, so we now have our W3, and so we're getting there. We're almost there. We have our basis B prime, which is an orthogonal basis, right? So our orthogonal basis is made up of W1, W2, and W3, which is what? Is that W1 was 1, 0, 0. W2 was 0, 1, 1. And then W3 ended up being 0, 1, negative 1. So this is an orthogonal basis. Orthogonal basis. But we need to find an orthonormal basis, right? So how would I do that? Well, I have to find all of the magnitudes of the W's, right? So, well, where are these W's again? I've got some room up here. So here we'll have what? Well, U1 is going to be W1 divided by the magnitude of W1. So now I'm getting a unit vector for each of these. So that's going to be, well, 1, 0, 0 divided by 1, which is just 1, 0, 0. Cool, cool? So U1 equals W1. Now, U2 will be W2 divided by the magnitude of W2. So W2 was 0, 1, 1. So that's going to be the vector 0, 1, 1 divided by the square root of 1 squared plus 1 squared. So that would be root 2, right? So we would get 0, 1 over root 2, 1 over root 2, or you can rationalize it. And then U3 will be W3 divided by the magnitude of W3, which is, so W3 was what? 0, 1, negative 1. Over the magnitude of 0, 1, negative 1. Again, we'll have 1 plus 1. So we'll end up with 0, 1 over root 2, and then negative 1 over root 2. Cool, cool? So, B double prime then is 1, I'll do it, both show both things. So U1, U2, and U3, which happen to be equal to 1, 0, 0, 0, 1 over root 2, 1 over root 2, and then 0, 1 over root 2, and then negative 1 over root 2 is an orthonormal basis. And it's an orthonormal basis. Cool, cool? All right, so we'll box this one because that's what we were looking for at the end of the day. All right, so that's it for today. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what you're seeing, please subscribe. Tell your friends. Bye.